For more than 300 years, the coastline of the Pacific Northwest has been holding its breath. Beneath the cold gray water off Oregon, Washington, and British Columbia, a giant slab of the Earth's crust has been locked in silence since the year 1700. Scientists have spent decades studying this fault, the Cascadia subduction zone, trying to figure out when it will finally give way. But when a research team pulled a long tube of mud up from the seafloor and looked closely at the layers inside, they found something that was in completely the wrong place. And what that mistake ended up revealing about the next great earthquake is genuinely alarming. To understand why, you have to understand what Cascadia actually is. Off the coast of the Pacific Northwest, there's a boundary where two enormous pieces of the planet meet. On one side sits the North American plate, the slab that carries cities like Seattle, Portland, and Vancouver. On the other side sits a smaller oceanic plate called the Juan de Fuca plate. And at this boundary, the oceanic plate is slowly diving underneath the continent, sinking down into the hot mantle below. Geologists call that process subduction. It's one of the most powerful engines on Earth. It builds mountain ranges, it feeds volcanoes, and every so often, it produces the largest earthquakes this planet is capable of making. The Cascadia subduction zone stretches roughly 700 miles, running all the way from Northern California up past Oregon and Washington and into British Columbia. That's a fault line longer than the entire state of California. And here's the part that keeps seismologists up at night. When a subduction zone this large ruptures along its full length, it doesn't produce a normal earthquake. It produces a magnitude 9 or even larger. That's the same class of earthquake that devastated Japan in 2011 and Sumatra in 2004. We're not talking about cracked plaster and broken windows. We're talking about the ground shaking violently for 4, 5, even 6 minutes straight, followed by a wall of ocean water racing toward the shore. For a long time, most people living in the Pacific Northwest had no idea any of this was there. The fault sits offshore, hidden under miles of seawater. It doesn't produce the constant small tremors that California gets. In fact, Cascadia is eerily quiet. It barely twitches. And that silence fooled everyone for centuries into thinking the region was relatively safe. It was not safe. It was loading. To picture what loading really means, imagine the Jafuca plate creeping eastward under North America at roughly 3 to 4 centimeters a year. That's about the speed your fingernails grow. It sounds harmless, almost gentle, but the front edge of the two plates, the part closest to the coast, is stuck. It's locked together by friction, refusing to slide, while the deeper part keeps getting dragged down. So, year after year, decade after decade, the locked zone bends and compresses like a diving board being pushed down at the tip. The coastline of Oregon and Washington is actually being squeezed and lifted a tiny bit right now this very year, warping under the strain. When the locked zone finally fails, all of that stored bending snaps back in seconds, and that violent rebound is the earthquake. And here's a detail most people outside the region never learn. Cascadia isn't even the only earthquake threat in the Pacific Northwest. There are actually 3 different kinds of quakes that can hit. There are the deep earthquakes that happen inside the sinking plate itself, far underground, like the magnitude 6, 8, Nisqually earthquake that rattled Seattle in 2001. There are shallow crustal faults running directly under cities. And then there's the big one, the mega thrust rupture of the whole subduction zone. Scientists actually put the odds of a strong deep quake under the Puget Sound region at around 85% in the next 50 years. So even before you get to the magnitude 9 monster offshore, the region is already sitting on a stack of loaded guns. Cascadia is just the largest one. The evidence of just how dangerous Cascadia can be was buried in plain sight, and it took an almost unbelievable piece of detective work to uncover it. Because Cascadia's last great earthquake didn't happen in the age of seismographs and satellites. It happened on the night of January 26th in the year 1700, more than a century before Lewis and Clark ever reached the Pacific. There were no instruments to record it, no cameras, no written accounts from the people who felt it most. And yet scientists today can tell you almost the exact hour it struck. That story is one of the most remarkable pieces of geological detective work ever assembled. And it starts on the other side of the world. On the coast of Japan in the year 1700, villagers along the shore of Honshu woke to the sea suddenly rising. Waves surged inland without warning, flooded rice fields, smashed boats against the docks, and damaged homes. Japanese officials who kept careful written records wrote it all down. But there was something deeply strange about this wave. Every tsunami they had ever recorded came right after the ground shook. This one didn't. Nobody in Japan had felt an earthquake at all. The wave had simply appeared out of a calm ocean as if from nowhere. For nearly 300 years, historians called it the orphan tsunami. A wave with no parent, a disaster with no origin. The mystery sat unsolved until the 1990s when a Japanese seismologist named Kenji Satake began pulling on the thread. He and his team went back through those centuries-old records, measuring the height of the wave and the exact time it struck the Japanese coast. Then, they did something clever. They worked backward. If a tsunami takes roughly 9 to 10 hours to cross the entire Pacific Ocean, then whatever earthquake created this wave had to have happened about 10 hours before it reached Japan somewhere on the far side of the ocean. And when they traced the timing and the wave's behavior across the water, the arrow pointed straight at the Pacific Northwest coast of North America. But a theory needs proof on the ground. And the proof was waiting in the forests of Oregon and Washington. Along the coast there, an American geologist named Brian Atwater had been studying something haunting. Entire stands of cedar and spruce trees standing dead in the salt marshes, their bare trunks reaching up out of the mud like gray skeletons. Locals called them ghost forests. These were trees that had once grown on dry, solid coastal land. So how did they end up drowned in seawater? The answer was chilling. When Atwater and other scientists studied the tree rings, they found that all of these trees had died at almost exactly the same time. The last ring each tree grew was in the year 1699, which meant they had all died sometime during the winter of 1699 into 1700. Not one by one, over decades all at once. Something had killed an entire coastal forest across hundreds of miles in a single event. Here's what happened. When the Cascadia Fault ruptured that night, the coastline didn't just shake, it dropped. In an instant, the land along the coast subsided, sinking down by as much as 1 to 2 m, 3 to 6 feet all at once. Land that had been dry forest was suddenly below the reach of the tides. Salt water rushed in and poisoned the roots, and the forests died where they stood. Those ghost trees are a photograph of the exact moment the ground fell. You can still visit them today. At places like the Nescoan Ghost Forest on the Oregon coast and the marshes near Capellas in Washington, where Brian Atwater did his key work, the weathered stumps still stand in the mud 3 centuries after the sea killed them, silent witnesses to the last time the giant moved. It's worth being honest here because good science invites argument. Not every scientist agrees on exactly how to read every layer in the mud. And there's a real ongoing debate about whether every turbidite was triggered by an earthquake, or whether some could come from storms, floods, or other underwater disturbances. Correlating deposits hundreds of miles apart and dating them precisely is genuinely difficult work. And researchers push back on each other's interpretations all the time. That debate is a feature, not a flaw. It's how the picture gets sharper. But even the skeptics agree on the core facts. The 1700 earthquake happened. It was enormous. And Cascadia has produced many others like it. The disagreements are about the fine print, not the threat. And there was a third source, one that had been telling the story all along. The indigenous peoples of the Pacific Northwest carried oral histories passed down through generations of a terrible night when the ground shook and the sea rose and swallowed entire villages. On Vancouver Island, stories told of coastal communities that were destroyed while people slept. For 3 centuries, these accounts had been dismissed as legend. But when the ghost forests, the Japanese records, and the oral histories were laid side by side, they all pointed to the same night, January 26th, 1700. At roughly 9 in the evening, a magnitude 9 earthquake followed by a tsunami that crossed an entire ocean. Clear's throat, the legend was a memory and it was accurate. That discovery changed everything about how scientists saw the region, because if Cascadia did it once, it will do it again. The only question is when. That question turns out to be far harder to answer than anyone would like. When geologists dug deeper into the mud along the coast and the deep sea floor, they found that the 1700 earthquake was not a one-time event. It was the latest in a long series stretching back thousands of years by counting the layers of ancient debris left behind by past quakes. Researchers pieced together a rough timeline. Over the last 6,000 years or so, the Cascadia subduction zone has produced roughly a dozen or more major earthquakes. On average, that works out to one enormous quake every 500 to 600 years. Now do the math on that and you start to feel the weight of it. The last one was in 1700. That was over 300 years ago. We are already deep into the window. But here's the frustrating truth about that average. It's just an average. The actual gaps between Cascadia earthquakes have been wildly irregular. Some have been separated by as little as 200 years, others by as much as 1,000. So the fault is not a clock. It doesn't go off on schedule, which means scientists can't tell you it will happen in a specific year. And they're careful to say the fault is not technically overdue in a mathematical sense, but they can tell you this. The strain has been building for more than 3 centuries. The Juan Defeca plate keeps pushing under North America a couple of centimeters every year, and the fault stays locked, storing that energy like a spring being wound tighter and tighter. Eventually that spring lets go. And the deeper you dig into that history, the more unsettling the pattern becomes. The turbidite record on the ocean floor stretches back roughly 1,000 years. And within it, scientists have counted around 19 or 20 full-length ruptures of the entire Cascadia margin, plus many more that only broke the southern portion. But those earthquakes didn't arrive at neat, even intervals. They came in clusters, long stretches of relative calm, then bunches of major quakes packed closer together, then calm again. Some researchers argue that after the year 1700, we may still be sitting inside one of those active clusters which would push the real near-term odds higher than the simple average suggests. Others are more cautious. What almost everyone agrees on is that 300 years of silence is a lot of stored energy, and the record makes it very clear that Cascadia does not stay quiet forever. So what are the actual odds? This is where the numbers get uncomfortable. Scientists break Cascadia into scenarios. If only the southern portion of the fault ruptures, you get an earthquake somewhere between magnitude 8 and 8.6, that's still a catastrophe. And researchers put the chance of that southern rupture at somewhere around 37 to 43% within the next 50 years. Read that again. Close to a coin flip over the span of a single human lifetime. If the entire fault lets go at once, a full margin rupture from California to British Columbia, you're looking at magnitude 8.7 to 9.2. And estimates put that at roughly 10 to 15% in the next 50 years. Lower odds, but the consequences are almost beyond description. In 2015, a writer named Catherine Schultz published an article in The New Yorker that put all of this in front of the general public for the first time. It won a Pulitzer Prize, and it contained a line that became infamous. A FEMA official describing what would happen when the full Cascadia rupture hits said that everything west of Interstate 5 would be toast. Interstate 5 runs right through the heart of Seattle and Portland. West of that line is where a huge share of the population lives. That single sentence turned a quiet academic concern into a regional nightmare that people finally started talking about. If you want to know why scientists take Cascadia so seriously, look at what happened in Japan on March 11, 2011. That day, a magnitude 9 mega thrust earthquake ruptured the seafloor off the Tohoku coast on a subduction zone that behaves a lot like Cascadia. It shook for minutes and launched a tsunami that swept miles inland, killing around 2,000 people and triggering the meltdown at the Fukushima nuclear plant. And here's the part that genuinely rattled the scientific community. That fault wasn't supposed to be capable of a full magnitude 9. The models had underestimated it. The section that ruptured broke through boundaries that experts had assumed would stop it, and the tsunami overtopped seawalls that had been engineered based on the old, smaller estimates. Tohoku was a brutal lesson in humility. It showed that subduction zones can rupture bigger and behave more violently than the tidy models predict. And when researchers looked back at Cascadia through that lens, the resemblance was uncomfortable. Same kind of fault, same magnitude, 9 potential, same offshore tsunami threat aimed at a populated coastline. The Pacific Northwest was essentially looking at a preview of its own future playing out in real time on the other side of the ocean. Everything scientists have done since, including the 2 discoveries at the center of this video, has been shaped by that wake-up call. When a fault surprises you at the cost of 2,000 lives, you stop assuming you know its limits. And that was the state of knowledge for years. A silent overdish giant off the coast capable of a magnitude 9 with roughly a 1 in 3 chance of a major rupture in a lifetime. Frightening enough. But recently, 2 separate teams of scientists found things that made the picture more complicated and in some ways more alarming than before. The first discovery came from an accident. And to understand it, you have to know how scientists read earthquakes that happened thousands of years ago. Here's the trick. When a massive earthquake strikes underwater, it doesn't just shake the seafloor. It triggers underwater landslides along the continental slope. Sediment that has been sitting on the ocean floor for centuries suddenly gets knocked loose and comes roaring downhill in a dense underwater current, spreading out across the deep-sea floor before slowly settling. That settled layer of debris is called a turbidite, and it has a very specific signature. As the underwater avalanche slows down, the heaviest coarse sand settles out first at the bottom. Then, finer and finer particles drift down on top, ending with a fine silt cap, a coarse on the bottom, fine on top. That's the fingerprint of a single earthquake frozen in the mud. Stack those turbidites up over thousands of years and you get a layered record like tree rings, but made of sediment. 1 earthquake, 1 turbidite. Count them, date them with radiocarbon, and you can reconstruct the entire earthquake history of the fault. A geologist named Chris Goldfinger at Oregon State University spent decades of his career doing exactly this, mapping Cascadia's past by reading the mud on the ocean floor. He is one of the people who helped build the modern picture of the fault, and in 1999 on a research cruise off the coast, his team made a mistake that would take more than 20 years to fully understand. While collecting sediment cores off Oregon and Northern California, the research ship drifted off course. It ended up about 55 miles south of Cape Mendocino in Northern California near a chaotic tangle of fault lines called the Mendocino Triple Junction. This is where the Cascadia system meets the northern end of the famous San Andreas Fault. The team had drifted right out of the Cascadia zone and into San Andreas territory. Now, plenty of researchers would have simply repositioned the ship and moved on. Instead, they decided that since they were already there, they might as well drop the sing tube and pull up a sample. It seemed like a minor detour. It turned out to be one of the most important cores they ever collected. That spot they drifted into is worth pausing on because the Mendocino Triple Junction off Northern California is one of the most seismically restless places in the entire lower 48 states. It's the exact point where three tectonic plates grind against each other, where the Cascadia subduction zone hands off to the northern tip of the San Andreas Fault. The seafloor there is a tangle of overlapping faults constantly shuddering with small earthquakes. So of all the places on Earth for a research ship to accidentally drift, this was the one spot where the records of two different great fault systems might actually be layered together in the same mud. The accident in hindsight dropped the SING tube into the one location that could reveal how Cascadia and the San Andreas talk to each other, because when they examined that core, something was wrong. The turbidite inside it broke the rule. Remember? Coarse sand is supposed to settle at the bottom and find silt on top, but in this core near the Mendocino Triple Junction, the pattern was flipped. The coarse sandy material was sitting on top of the finer silty sediment. As Goldfinger later described it, they had all the sand at the top, which is simply not where it's supposed to be. It was as if gravity had run backward. For more than 2 decades, that anomaly sat there unexplained, an oddity in the data that didn't fit any clean story. If you're finding this deep dive fascinating, take a second to subscribe. This channel breaks down the geology and disasters shaping our world every single week, and there's a lot more coming. Now, back to that impossible core, because the explanation the team finally landed on is the part that should make everyone on the West Coast pay attention. After years of work, Goldfinger and his colleagues realized the answer. That single strange layer wasn't one turbidite at all. It was 2 stacked almost on top of each other, so close together that they looked like one confused deposit. The lower finer layer had settled, first laid down by an earthquake on the Cascadia subduction zone. And then before that fine material had even finished settling out, a second underwater avalanche came through and dumped the coarse sand on top. A second earthquake. And that second earthquake had come from the San Andreas Fault right next door. 2 of the most feared fault systems on the west coast of North America, firing so close together in time that their debris piled up in the same tube of mud. That raised an enormous question. Was this a fluke, a one-time coincidence where 2 nearby faults happened to slip around the same era, or was it a pattern? So the team went back through the sediment record comparing the paired deposits found north and south of Cape Mendocino. And they used radiocarbon dating to pin down when each one formed. And what they found is the headline. Over the past 3,000 years, roughly half of the earthquakes on the southern Cascadia subduction zone appear to be timed together with earthquakes on the northern San Andreas Fault. Many of those paired deposits formed at nearly the same moment within the limits of what radiocarbon dating can even measure. That synchronicity happened far too often to be random chance. Let that shape the picture in your mind. For years, people imagined the 2 great West Coast disasters as separate threats. The Cascadia megaquake in the Pacific Northwest and the San Andreas earthquake in California, as if they lived in different worlds and would arrive on different days. This new research suggests that assumption may be wrong. When the southern end of Cascadia ruptures, the violent shaking and the sudden shift of stress along the coast can reach the northern San Andreas and shove it past its breaking point. The San Andreas can follow within minutes or hours, sometimes maybe longer. The big one, in other words, might not come alone. Think about what that means for emergency response. The entire disaster plan for the West Coast assumes that when one region gets hit, the neighboring regions can send help. Rescue crews, hospitals, supplies, National Guard, all flowing in from the areas that are still standing. But if Cascadia and the northern San Andreas can rupture in the same afternoon, then Northern California and the southern Pacific Northwest could both be crippled at the same time. Instead of one shattered region reaching out to intact neighbors, you get multiple regions collapsing simultaneously, each one too broken to help the others. Highways down, bridges gone, ports destroyed all at once across a much wider stretch of coast than anyone had planned for. This is what scientists mean when they say the finding is alarming. It isn't just a bigger earthquake. It's the possibility of overlapping catastrophes stacked on top of each other. And here's the sobering part. This discovery didn't come from some dramatic new event. It came from a decades-old SING accident in patient work in a lab. The synchronization has probably been happening for thousands of years. We just never had the evidence assembled clearly enough to see it. The fault didn't change. Our understanding of it did. And that brings us to the second discovery, which comes at the same problem from a completely different direction, because while one team was reading the fault's past in the mud, another team went looking at the fault structure itself deep beneath the seafloor. What they found suggests the Cascadia zone is not the simple single solid slab that textbooks have described for decades. In 2021, researchers launched an ambitious project called the Cascadia Seismic Imaging Experiment. A research vessel named the Marcus G. Langeth spent weeks off the coast towing equipment that sends powerful sound waves down into the seafloor and listens for the echoes, building a kind of ultrasound image of the rock structures buried below. This was the most detailed look anyone had ever taken at the guts of the Cascadia subduction zone, and off the coast of Vancouver Island, at the northern end of the fault, the images revealed something that stunned the team. The subducting oceanic plate wasn't a single clean, intact sheet sliding smoothly under North America. It was tearing. The seismic images published in the journal Science Advances in 2025 showed that the plate is fracturing and breaking apart into pieces. In the far north, the Juan Fuca plate and a smaller neighboring plate called the Explorer plate are literally ripping away from each other. The researchers, led by scientists including Brandon Shuck at Louisiana State University, described it as catching a subduction zone in the act of dying, not collapsing in one violent moment, but coming apart slowly, one fragment at a time, like a train derailing car by car in extreme slow motion. What makes this discovery so valuable is that scientists have almost never gotten to watch a subduction zone die in real time. Usually we only find the corpses. The fossil fragments of ancient plates scattered across the seafloor like the shattered remains of the old Ferrarolon plate down near Baja, California. Researchers had long suspected those fragments were the leftovers of dying subduction zones, but they couldn't see the mechanism. Cascadia is now offering a live demonstration, and as each piece of the plate tears free, it can open what geologists call a slab window, a gap where hot mantle material rises up toward the surface. That rising heat can fuel bursts of volcanic activity in unexpected places, and over millions of years it reshapes not just the fault, but the volcanoes and coastline of the entire region. We are, in a very real sense, watching the geography of the future Pacific Northwest slowly being redrawn. When that finding hit the news, a lot of people had the same hopeful reaction. If the fault is dying, if the plate is falling apart, does that mean Cascadia is shutting down? Does that mean the threat is finally going away? It would be a comforting thought for the millions of people who live in the shadow of this fault. But scientists were quick and firm in correcting that hope. The process they imaged is real, but the time scale is almost impossible to feel. This tearing and dying of a subduction zone doesn't play out over years or decades or even centuries. It plays out over millions of years, on any time scale that matters to a human being. To your children, to your grandchildren, to their grandchildren, Cascadia remains fully active and fully capable of producing a magnitude 9 earthquake. The plate winding down over geological time changes nothing about the danger next week, next year, or next century. In fact, the reality is more complicated than either shutting down or business as usual. What the imaging really showed is that Cascadia is segmented. For a long time, scientists treated it as one continuous plate boundary, a single zip line running the whole 700 miles. But the new data shows it's broken into structurally distinct segments divided by tears and fractures in the slab. Modern mapping has identified multiple segments along the fault, and this segmentation cuts in two directions at once, which is exactly what makes it so hard to reason about. On one hand, segmentation could be good news. If the fault is chopped into separate blocks by these tiers, then maybe a rupture that starts in one segment gets stopped at the boundary, unable to jump the gap into the next. That would limit some earthquakes to a single segment, keeping them smaller than a full margin monster. But on the other hand, segmentation could be bad news because those same fractures can concentrate stress in unexpected places. Smaller plates and microplates can rotate grind against each other and transfer strain across the region in ways that are genuinely difficult to predict. A boundary that seems like it should stop a rupture might instead redirect it or load up a neighboring segment until it fails too. Scientists are still working out which of these behaviors dominates, and that uncertainty is not reassuring. When one of the largest faults on the continent turns out to be more complex than the models assumed, more complex usually means harder to forecast, not safer. There's another detail buried in that segmentation research that deserves attention. The segment of Cascadia that runs from Washington up into British Columbia is, according to the scientists studying it perfectly, capable of producing a full magnitude 9 amount of slip entirely on its own. So even in a world where the fault is broken into pieces, individual pieces are still large enough to level a region. Segmentation doesn't shrink the threat down to something manageable, it just reshuffles it into a form we understand even less well than before. So step back and look at where these two discoveries leave us. On one side, the sediment record says Cascadia and the San Andreas may fire in tandem, threatening two regions at once. On the other side, the seismic imaging says the fault itself is fractured, segmented, and evolving in ways that scramble our neat-old models. Neither of these findings lowers the danger. Both of them tell the same underlying story. The system is more intricate, more interconnected, and less predictable than we believed even a few years ago. And it's still loaded with over 3 centuries of stored energy. Now, what does the actual event look like when it finally comes? Because it's easy to say magnitude 9 and let the number wash over you. Let's make it concrete. When the full Cascadia Fault ruptures, the first thing people will notice is that the shaking does not stop. A normal earthquake lasts a handful of seconds. A Cascadia full margin rupture could shake the ground continuously for 4 to 6 minutes. Minutes, long enough that people describe not being able to stand watching in disbelief as it keeps going and going. During that time, older buildings, bridges, overpasses, and unreinforced structures across the region would be pushed far past what they were built to survive. Then comes the water. The same fault motion that shakes the land also shoves the seafloor upward, displacing a colossal volume of ocean and launching a tsunami. And because Cascadia sits just offshore, the coastal communities of the Pacific Northwest would have almost no warning. In some places, the first tsunami waves could reach the shoreline in as little as 15 to 30 minutes after the shaking stops. That is not enough time to drive inland. For people on the coast, survival would depend on being on foot and moving to high ground immediately, in the chaos right after the longest earthquake of their lives. Meanwhile, that same coastline could once again drop by several feet in an instant, exactly as it did in 1700, turning dry towns into flood zones before the wave even arrives, and the tsunami wouldn't stay local. Just as the 1,700 wave crossed the entire Pacific and struck Japan 10 hours later, a modern full Cascadia rupture would send a tsunami racing across the ocean toward Hawaii and back toward Japan. It's the mirror image of the orphan tsunami, except this time the parent earthquake would be recorded by thousands of instruments the instant it happened. And coastal warning sirens would sound from Honolulu to the coast of Asia. The ocean that carried the evidence of the last Cascadia quake to Japanese record-kei keepers 3 centuries ago would carry the next one right back to them. That is the reach of a single subduction zone letting go. The FEMA scenarios for a full Cascadia rupture describe a level of disruption that's hard to hold in your head. Widespread collapse of infrastructure west of Interstate 5. Bridges and highways severed, cutting coastal communities off from the rest of the country. Ports and airports damaged. Water power and communication lines down across a vast area in some places for weeks or months. Thousands of people potentially killed by the shaking and the tsunami, and hundreds of thousands displaced. This is not a fringe doomsday fantasy. It is the mainstream planning scenario that emergency agencies across Oregon, Washington, and British Columbia are actively preparing for right now. In fact, they've rehearsed it. In 2016, a massive multi-state drill called Cascadia Rising brought together FEMA, the military, and emergency crews across the Pacific Northwest to simulate exactly this event of full margin magnitude 9 rupture and the tsunami that follows. The simulation assumed the coastal region would essentially be cut off with roads and bridges destroyed, survivors stranded, and supplies unable to reach them by land for days or longer. The exercise wasn't about preventing the earthquake. It was about confronting a brutal reality. When it happens, huge stretches of the coast will be on their own, and help may not arrive for a long time. That's why officials tell coastal residents to be ready to survive independently for at least 2 weeks, not the usual 3 days. The projected damage is staggering. Analysts have estimated a full Cascadia rupture could kill thousands of people, injure tens of thousands more, and leave hundreds of thousands of buildings damaged or destroyed across a region home to millions. The economic toll runs into the tens of billions of dollars, and full recovery for the hardest-hit coastal zones could stretch across years, even decades. Some low-lying towns that get inundated by the tsunami might never be rebuilt in the same place at all. This is the scale of event we're talking about. Not a bad day, a generational reset for an entire corner of the continent, and here's the psychological trap in all of this. The thing that makes Cascadia so uniquely dangerous. It's the silence. Because the fault sits quiet for centuries between ruptures, it's incredibly easy to forget it's there. There are no regular reminders, no monthly tremors to keep the fear fresh. Generations are born, live, and die without ever feeling it move. And that quiet gets mistaken for safety. But the quiet is not the absence of danger. The quiet is the danger. It's the sound of a spring being wound tighter year after year with no release. The longer Cascadia stays silent, the more energy it stores and the bigger the eventual snap. So, what are scientists actually doing about it beyond ringing the alarm? Quite a lot. As it turns out, along the west coast, an earthquake early warning system called Shake Alert is now operating. It uses a network of seismic sensors that can detect the very first fast-moving waves of an earthquake and send out an alert a few seconds to a few tens of seconds before the violent shaking arrives. That sounds tiny, but a warning of even 15 or 20 seconds is enough time for trains to slow down, for surgeries to pause, for school children to drop and take cover, and for automated systems to shut off gas lines and open firehouse doors before they get jammed shut. Researchers are also working to extend monitoring offshore closer to the fault itself, dropping instruments onto the deep sea floor to catch the earliest signs of trouble and to better understand how the locked zone behaves. There's one more thing scientists watch, and it's strange enough that it deserves its own moment. Even though Cascadia is silent in terms of ordinary earthquakes, the deep part of the fault is not completely still. Every 14 months or so, roughly, The lower section of the subduction zone quietly slips, not in a violent jolt, but in a slow, silent creep that unfolds over days or weeks and releases the energy of a decent-sized earthquake without any shaking anyone can feel. These are called slow slip events, or episodic tremor and slip. And they were only discovered in the last couple of decades using extremely sensitive GPS stations that detected the ground drifting in the wrong direction. During these events, the deep fault glides forward and loads a little extra stress onto the locked zone above it. The same locked zone that will one day produce the megaquake. Scientists still don't know whether one of these quiet, slow slip events might eventually be the trigger that tips the whole fault over the edge. So every time Cascadia whispers, they listen very carefully because it's the closest thing we have to hearing the giant breathe. At the same time, the two discoveries we've talked about are feeding directly back into the hazard models that shape building codes and evacuation plans. The synchronization and finding forces, planners to consider scenarios where multiple regions go down together. The segmentation imaging helps refine which parts of the fault might rupture, how far a rupture could travel, and where the shaking would be worst. Every piece of this research, even the discoveries that sound frightening, ultimately makes the region a little more ready. Knowledge doesn't stop the earthquake, but it can absolutely change how many people survive it, and that survival is already being engineered into the region one project at a time. Across Oregon and Washington, older buildings, bridges, and schools are slowly being retrofitted with steel and reinforcement so they can ride out minutes of shaking instead of collapsing. On the coast, communities are building vertical evacuation structures, tall, reinforced platforms and towers designed so that people who can't outrun the water can climb up above it. In the 15 minutes, they'll have a school district in Westport, Washington built one of the first structures of its kind in the country. A gymnasium engineered to double as a tsunami refuge that lifts hundreds of children above the wave. Meanwhile, the shake alert warning now reaches ordinary people directly pushed straight to the phone in your pocket so that the seconds of warning aren't locked away in a lab but delivered to the person standing in the kitchen. None of this makes the region earthquake-proof. Nothing can. But every retrofitted bridge and every evacuation tower is a bet that when Cascadia finally moves, more people will still be standing when the shaking stops. There's something almost humbling about this whole story. We tend to think of the ground beneath our feet as the definition of stability, solid, permanent, the one thing you can count on. But the Cascadia subduction zone is a reminder that the ground is alive and moving and vastly more complicated than we assumed. A fault we thought was a single simple slab turns out to be tearing itself into pieces. Two disasters we thought were separate turn out to be quietly linked across 3,000 years of history. And the calmest, quietest stretch of coastline in the country turns out to be the one holding the most dangerous secret. Every time scientists look closer, Cascadia turns out to be stranger and more formidable than the last time they looked. The most unsettling truth is also the simplest one. The earthquake that struck in the year 1700 will happen again? That is not a maybe. It is a certainty written into the physics of the fault. The only real unknowns are when it arrives, how far it spreads, and whether it drags its neighbor down with it. For the millions of people living between the Pacific and Interstate 5, the smartest response isn't panic, and it isn't pretending the quiet means it's gone. It's preparation, knowing your evacuation route, keeping supplies ready. Understanding that if the ground ever shakes for longer than you think an earthquake should, and you're near the coast, you move to high ground without waiting for anyone to tell you to. Because someday off the coast of the Pacific Northwest, that locked and silent fault is going to let go. The mud on the ocean floor already told us it happens. The ghost forests already showed us what it does. And now the newest science is telling us it might not come quietly and it might not come alone. The coast is beautiful. It is also on borrowed time, and the ocean has been keeping the secret for 300 years waiting. If this breakdown gave you a new respect for the ground under your feet, subscribe and stick around because the planet has a lot more of these hidden stories, and we're going through them one at a time. Take care of yourselves out.